Good morning, students. It is a new attempt from our end to communicate to you and teach you certain concepts online. Due to compulsions of time, where physical classroom interaction has become difficult, we are reaching out to you through this channel. I hope this new way of teaching learning method will definitely be useful to you. Today we are going to discuss about the shear strength of the soil. This title has got two words, shear and strength. Let us try to understand these two words before proceeding further. Shear or the shear force is the unbalanced force at any cross section of the material. The shear force causes shear stresses. The shear stresses are in plane stresses or tangential stresses. With increase in the unbalanced force or the shear force across the section, the shear stresses also increase, and at a certain load, the stresses may reach their maximum value that the cross section of the material can offer. Any increase beyond this point would lead to the failure in shear. The maximum shear stress that any cross section of a given material can offer just before failure is called its strength in shear or shear strength. The application of concept of shear to the soils can be better understood with the help of a block friction. Consider a block of certain weight W resting on a horizontal surface. N is the reaction. If this block is pulled by a force F, it is obvious that a frictional resisting force gets developed at the interface between the block and the surface in a direction opposite to the direction of applied force. This frictional force Fs increases with increasing pulling force F up to a certain limit. Thereafter, the block starts moving. That is, it overcomes the frictional resistance Fs at the interface. The magnitude of the frictional force being Fs, that is equal to mu into N, where mu is the coefficient of friction between the contact surfaces. This force is directly proportional to the reaction N. If the weight of the block is increased, the reaction N would also increase. Now, the corresponding frictional force would be greater than that in the previous case. From these two illustrations, it is obvious that the frictional force is a function of the reaction N, which in turn is the function of the weight of the block. As the weight of the block increases, the interlocking or of the roughnesses at the surface also increases, leading to the greater frictional force to overcome the resistance. Comparing this analogy with a soil sample in friction, consider a soil mass contained in a system with two halves, subjected to a normal stress and a shear stress. With a normal stress, when tried to shear, certain amount of shear stress tau gets developed before failure. If this normal stress is increased, the maximum shear stress required to fail the sample also increases. Thus, when the results of different normal stresses and their corresponding shear stresses are plotted, we get a failure envelope which is a straight line. When this straight line is extended, the y-intercept is obtained. This y-intercept represents cohesion or cohesion intercept C of the soil. The slope of the straight line represents the angle of internal friction or angle of internal resistance phi. It is noted here that the equation of the line is a straight line equation y is equal to mx plus c, where y represents the shear stress tau, m represents the slope of the line, that is tan phi, and x represents the normal stress acting on the surface, and c is the cohesion or y-intercept. This concept is further explained in the Coulomb's concept of shear strength. Then why study the shear strength of the soils? The study of the shear strength of soils is essential to establish the stability of various earth or earth retaining structures such as slopes, retaining walls, foundation bearing capacity, etc. The slide shows a man-made slope or an embankment or an earth dam slope. The slope line ABCD fails under certain critical conditions such as sudden drawdown condition for upstream slopes of the earthen dam or steady seepage condition for downstream slope of the earthen dam, or just after construction case for both earth dam and embankments. It is noted here that under any given critical conditions, the soil mass in a slope fails along a circular surface such as AED. The mass of the soil bound by A, B, C, D, E, A moves under the action of the gravity, thus shearing or cutting it off from the rest of the soil mass. We need to evaluate the shearing stresses and shear strength along these curved failure surfaces. The next slide shows a retaining wall retaining earth. Retaining walls are used to retain the soils, and the movement of these walls induce critical shearing zones in the retained earth behind them. The soil mass contained in an approximate wedge behind the wall slips along a failure surface, thus shearing or cutting it off from the rest of the soil masses. We need to evaluate the earth pressure acting on these retaining structures for its safe design. The evaluation of strength of the soil helps in achieving the same. Next, many slopes on the surface of the earth are naturally formed, which are either finite or infinite in nature. The evaluation of safety of these natural slopes becomes essential to protect the infrastructural facilities such as highways, railways, etc., and also the habitations. The study of the shear strength of soil helps in achieving the same, as well as in taking some remedial measures such as ground improvement techniques, etc. The next slide shows a foundation transmitting load to the underlying soil. The evaluation of shear strength in terms of bearing capacity is very essential for the foundation design. The application of the foundation pressure causes the development of shear zones below the foundation. To evaluate the nature of failure and provide analytical treatment to the bearing capacity, the shear parameters are very essential. Thus, these four examples show the importance of study of shear strength of soils. To sum up, we can conclude here that the development of shearing stresses in a soil mass under the different loading conditions lead to the sliding of soil mass, shearing it or cutting it off from the rest of the soil mass. The failure is along a weak plane or a shear plane that develops. There is a normal stress acting on the shear plane. The shear stresses reach the shear strength and the failure is imminent. It should be noted here that the failure plane is a weak plane along which the soil mass gets sheared. The shear plane never cuts the particles of soil as they are the hard soil particles. Microscopically, the shear plane follows a zigzag path, avoiding the hard soil particles and taking the path of least resistance. However, these planes follow the general shear failure patterns. With this brief introduction, let us proceed to study the shear strength of soils in detail.